In this video, we explore the two conditions that a rigid body must satisfy to be in equilibrium. By a rigid body, we mean an object that does not deform visibly, rather than one that is flexible or one that contains hinges. If one or more forces are applied to a rigid body like this cookie tray, they can cause translation and rotation. In our previous equilibrium video, Forces at a Point, we showed that a point will be in equilibrium if the vector sum of the forces acting on it is zero. If we shift these forces along their own lines of action and apply them to a rigid body, that body will also be in equilibrium. As we will see shortly, other combinations of applied forces can also produce equilibrium. In all of these cases, for the rigid body to be in equilibrium, the vector sum of the forces acting on it must be zero, exactly the same as for a point. When this condition is satisfied, the rigid body will not translate. Two equal and opposite forces would satisfy this first condition, but suppose we apply them like this. What do you think will happen? As you may have guessed, the body will rotate until the two forces line up with each other. To explain how forces can produce rotations, we need to introduce the idea of a moment, or a torque. Suppose we fix a point A on the model so that it cannot move. If we apply just the force F1, it will cause the wood shape to rotate clockwise about A. The force F2 would also generate a moment about A, but that moment would be smaller and counterclockwise. When the two forces act together, they produce a net clockwise moment. As the body rotates, the moments generated by the two forces change, and when they just balance, the body stops rotating and comes into rotational equilibrium. We usually state the second condition as the sum of the moments about any point must be zero. Two factors determine the magnitude of a moment. Can you guess what they might be? To answer this question, let's consider a beam supported by two hands near its center. If we place a weight on the right side, it causes this beam to rotate clockwise. Adding a second weight increases the moment that is generated. In addition, if we move a weight from one location to another that is further away from the supports, a greater moment is generated. Now, can you state what two factors determine the magnitude of a moment? The answer is force and distance. More specifically, we multiply force and distance together. The distance we use is the perpendicular distance from the line of action of the force to the point A. This is the same as the shortest distance between point A and the line of action of the force. By convention, we call moments that are counterclockwise positive and clockwise moments negative. Now consider a rigid body that carries three arbitrary forces. To determine if it will rotate, we can take moments about any point A. To calculate the moment created by the first force, we multiply its magnitude by the perpendicular distance from its line of action to A. As you can see, the moment from this force is counterclockwise, so we call it positive. We can do the same for each of the other applied forces, and we find that there is a net counterclockwise moment. When these forces are applied, the body clearly rotates counterclockwise, which is consistent with our calculations. As the body rotates, the perpendicular distances change. Eventually, the new distances are such that the total or net moment is zero. At that instant, the body stops rotating and it is in equilibrium. If we consider equilibrium of a point rather than a body, all of the distances in the moment calculation shrink to zero, and so the sum of the moments must be zero. That is why when we consider equilibrium of a point, we need only satisfy the sum of forces condition. The sum of moments criterion is automatically satisfied. It turns out that a body acted on by three forces will rotate until the lines of action of those forces pass through a common point. This relationship is known as the principle of concurrent forces, and it applies only to bodies that carry three forces. If you take moments about that common intersection point Q rather than about A, all of the perpendicular distances to the lines of action are zero, and it is obvious that the sum of the moments will always be zero. In fact, it is impossible to arrange those three forces in such a way that their lines of action do not cross at a common point. There is, however, one exception. Can you figure out what it might be? The exception arises when the three forces are parallel to each other. For a rigid body that carries more than three forces to be in equilibrium, the vector sum of those forces must add to zero, and the sum of the moments must also be zero. But as this example demonstrates, the lines of action of the forces may not intersect at a common point. And so we see that the principle of concurrent forces does not apply to bodies with more than three forces. For the cookie tray to be in equilibrium, the vector sum of the forces acting on it must be zero, and the sum of the moments that they produce must be zero. If you followed all of the concepts outlined in this video, you deserve a treat. We hope you will watch some of our other engineering models videos. Bye for now.